Hello again, everybody. So this was requested, so I wanted to just go ahead and do it. So we got a request to do a video solution of Chapter 8, Problem 77. And what I like about this problem is it really drives home the point as to what all of these variables represent and how to interpret them in a diagram. So we get calculate the torque about the z-axis. So all of these torques are going to be about the z-axis because I got my y and x-axis here. So my z-axis, my positive z-axis is going to go out of the page, right? It's going to go out of the page where the negative z-axis is going to go into the page. So we'll deal with that right-hand rule though later. So calculate the torque about the z-axis that is out of the page at the origin in the following figure that F1 is 3 newtons, F2 is 2 newtons, F3 is 3 newtons, and F4 is 1.8 newtons. So, and just a reminder to everybody of what these represent. So to calculate the magnitude of a torque, direction, either use the right-hand rule or you got to go back to kind of this cross product idea of what a torque is. So it's R cross F. But I recommend the right hand, just you can calculate the magnitude this way and then use the right hand rule to determine the direction. So again, this is the torque of any, so in any object that exerts a force, it's going to exert a torque. So technically I should have 1, 2, 3, 4 torques, although one of these is actually going to be a 0 torque, and we'll see why. And to get that torque, it's the r vector, right, which is the distance from the axis of rotation. So here's my axis of rotation right here. This is what's being denoted as my axis of rotation at the axis here. So it's the r vector, that's the distance from where the force is applied to the axis of rotation. So for F1, the r vector points like this. This vector right here would be my r vector. So it always points from the axis of rotation to where the force is being applied. And then the force itself, that's F1, so F1, the magnitude of the force, multiplied by sine of theta, where theta is the angle between R and F. So those vectors, the R vector and the F vector. Okay, so let's see what this looks like. So let's do it for torque 1. So we'll do it first for torque 1. So it's going to equal the R vector. Well, the R vector is this. I kind of already drew it last time. Well, it's already here for me, right? It's pointing this way. So this is the R vector, what they have here. And it's equal to, the magnitude is equal to 3 meters. So that's going to be 3 meters right there. And then I do the magnitude of the force vector. That's going to be F1, which is 3 newtons. So that's going to be 3 as well, times sine of the angle between these two vectors. And the angle between these two vectors, I would say, is about 90 degrees. I mean, I don't think they're trying to trick me or anything. That's pretty much 90 degrees. So this is sine of 90. So sine of 90 is equal to 1, and that means 3 times 3 is going to give me 9 Newton meters. So that's my torque. I'll deal with direction in just a moment. I'll deal with direction at the end. Let's just calculate the magnitudes first. So torque 2, that is over here. So again, the r vector is the distance. So the force is being applied right up here. The axis of rotation is down here. So my r vector is going to point from the axis of rotation to where the force is being applied. So that's going to really be just kind of this arrow itself. This is my, so this was R1. This is going to be R2. Let's throw it over here. R2. Anyway, okay. Then we got the, so R2 is going to be equal to 2 meters. That I got right here. And then multiplied by the force, well, the magnitude of the force F2 is 2 newtons. So that's going to be 2 right in there. Now the angle is where things are going to get a little bit tricky. So sine of the angle, I tend to go with, again, you can do some fancy geometry and you know, like you did in the Pivot Interactive and figure that out. I always just stick with it. It just never steers me wrong. I'm looking for this angle. That's the angle between those two vectors. So what's the angle between those two vectors? Well, I know this is 90 degrees. So it's going to be 90 minus 30, right? Because I know this is 30 degrees. So 90 minus 30, well, that's going to be 60 degrees. So this angle is now 60 degrees. So it's going to be sine of 60 is this angle here. I got to break out my calculator here because I don't know what sine of 60. It's rad, what, square root of 3 over 2 or something like that. Bah, I'll just do sine of 60 times 2, which gives me about 3.46 Newton meters. Again, we'll figure out direction at the end. So that is for torque 2. That's the magnitude. Torque 3. Here I could, identify everything, but if I look at this, right, the force is coming right out of the axis of rotation, right? So I have no r vector, basically. My r vector is equal to 0, and that basically means I'm going to have no torque, right? If r is equal to 0, I have no torque. 0 times anything is going to be 0. So my r vector for this is 0, therefore I have no torque. So you can exert a force, but still not exert a torque, depending on how you, right? There's all these subtleties in creating a torque. And if any one of these ends up being 0, you got no torque. So yeah, this one's going to be 0. And lastly, torque 4. So it's going to be the r vector. Hopefully you're getting the hang of this now. Distance from the axis of rotation to where the force is being applied, that's 2 meters. My force, if I look over here, it's 1.8 newtons. And then, my axis, my angle. I'm looking for my angle. So they give me this 20-degree angle. Again, they're trying to be tricky to me. So I'm trying to find out really this angle, because this would be my theta, my angle between the r vector and the force vector. Well, that's going to be, what is that going to be? 20, oh yeah, 90 minus 20. So that's going to be 70 degrees. So this would be sine of 70 right there like that. And so this is, so now plugging all this in. Gives me 3.38. Now, are they asking me to find the net torque? Calculate the torque about the z-axis that is out of the page at the origin in the following figure, given that. All right, sorry, just came back to try and see, because they're saying the torque about the z-axis. So they're saying that the positive z-axis is out of the page, which is pretty much what I established over here. That's all they're saying. So, and I guess they seem to want us to be calculating the net torque. So I wish this said net torque. So to get that net torque, all right, now we're going to need direction here, right? So torque 1, if I use my right-hand rule, so try it yourself. Start with your right hand on the axis, and then bring your fingers along the r vector, but then curl your fingers in the direction of F1, and you're going to see that this is going to give me a negative torque, because it's going to be a torque that's into the page. So that's going to give me a negative torque. So this is all going to be negative, and then I'm going to add all this up at the end, and that's going to give me, if I add all this up at the end, that's going to give me my net torque. Okay, torque 2 is this one. So if I use my right hand rule again, I get a positive torque out of this. I'm getting a positive torque out of this because it's pointing the positive z-axis. So it's going to be positive 3.46. 0, it's just going to be 0. It's not going to do anything, not contribute anything. And then torque 4, if I use my right hand rule, I'm going to get a negative torque again. So this is negative. And so I just now need to add these all up. So I got negative 9 Newton meters plus 3.46 minus 3.38, and I get negative 8.92 Newton meters. So the net torque points at 8.92 Newton meters in the negative z direction. So if I wanted to be really specific, I could write z hat as well, because I know that's the direction of the torque. So there we go. Hopefully that helped. All right. See you guys later. Bye.